Good evening, everyone. I trust we are all doing peachy. Just making sure I've got everything turned off that should be turned off and on that should be turned on. Okay, and I remembered to set myself to do not disturb this time. Okay, there we go. So, what have I been up to and what are we doing? Well, if you recall from the last stream, our code for generating procedural systems was huge and ugly and kind of stretched all the way across here. That has now been greatly condensed and improved. And we also had an issue where planets were generating inside the radius of LT and Y class stars. So that was the first thing that desperately needed fixing. So what I've done is I've really gone through and picked apart the proc gen code for the star systems to make it a lot more step by step and a lot more clear and concise and easy to follow. And as a result of that, it's more efficient and more stable. So let's just pick through that a minute. Like some of this is pretty much the same as it's always been, other than the fact I've color coded the star classes just for visualness. But on the star classes themselves, I've split up a lot of what was here and just basically condensed into macros. A lot of them are really, really simple macros as well, like that. It's just cleans it up a little bit. So essentially we're taking our radius from the galaxy gen. We're grabbing our volume from that. We're using that to derive our mass. And this is based on a fairly linear mass scale from main sequence stars. We're then converting that to kilograms, and then we're then defining the system mass from that, which is essentially I think 0.014% of the star's mass is used as the protoplanetary disk. That's essentially what Sol uses. So the mass of all the planets and everything in the Sol system is approximately 0.014% of the star's mass. We then randomly decide an age. And this actually, I'm going to be coming back to this because I think we're going to need some slightly more granular age numbers. So rather than storing it as billions of years, I might convert that to millions of years instead to make it more granular. We then calculate the density of the star, and then we finally calculate the Roche limit for the star. And for simplicity's sake, because we don't yet know the composition of the planets, we can't put in the planet density or whether or not it's a rocky or icy planet. So the Roche limit, I've taken the worst case scenario and gone with an icy planet and then just given it an average density. And that gives us our rough Roche limit for the star. It's certainly sufficient enough for drawing a line as to where or not planets can form. Once we've done that, we just define our temperature regions. We add all the details for the central star object, and that's messy, but this is essentially where we're writing all our descriptions and things. And again, that needs to be cleaned up and refined and made a little bit more verbose. But yeah, this is where we're procedurally going to construct all of the description for that body in the system. So when you go on the scanners, this is what it comes up with. We simply rotate it randomly to give it its inclination relative to the galactic plane, and then we go ahead and build the planets. And the bulk of this is now new compared to Wednesday. So essentially we've got our system mass. So this is the mass of the protoplanetary disk. And if there is mass remaining, then we need to add a planet. So we begin with determining the initial orbital distance. And with that, we basically check to see, is our current distance 0? If so, this is the first planet. And this is where we employ the Roche limit. So we take our Roche limit, we multiply that by the star's luminosity, because essentially we're simulating the effect of solar wind. So more massive, more luminous stars are going to be pushing that protoplanetary disk further out away from the star. So that's what we're doing here. And then we arbitrarily times that value by 100, and that's kind of the range in which our first planet can sit. And if it's not the first planet, then we just we use something which is not scientifically proven. I've called it the Blagg formulation, but it's actually a derivative of something else. Essentially, all of the planets in the solar system are essentially separated by about 1.7 of the previous planet's distance, and they're also that the same weird mathematical coincidence is true for Jupiter's moons as well. And it's something to do with, I think, orbital resonance and the way things establish in a disk of matter. But essentially each object is 1.7 times further away than the object previous to it. And that's not always true for exoplanet systems, but we're running with it for this for now, and we're just giving it a bit of variance. That's how we choose the position of the planet. We then determine our temperature. So this is our rough equilibrium temperature for the position that the planet is in the system. So this isn't the final temperature of the planet, this is our starting temperature. So if it was a perfect black body in space, this is essentially its temperature. And then now that we know the temperature, we can determine what type of planet it is. So we've got 4 base planet types: rocky, gas, ice giant, and icy body. I'm contemplating squeezing water world into this somewhere, because a true water world isn't like an Earth-like without any islands. A true water world has a very, very thick atmosphere, a very, very dense atmosphere, a very, very tall atmosphere, and a huge amount of water. They're not an Earth-like with no islands. They're kind of a separate planetary type in their own right. I might add them separately, or I will use the gas giant, at the low end of the gas giant, to create those, because these start mass-wise at 2 times the mass of Earth. So we can fold those into that perhaps. But essentially, we just take the Kelvin temperature and we use a curve, which I put together. I'm going to save this in a minute because, not save as, save all. I've noticed that it tends to crash when you load a curve, but if we try it and see, oh no, there we go. So the curves are the distribution of how likely these planet types are. So as you can see, this would be towards the star. As you move away from the star, the percentage chance for rocky planets decreases, because in the protoplanetary disk, the bulk of the heavy matter is by the star, and then that heavy matter dissipates more and more the further from the star you get, up into the frost line, which is here at 150 Kelvin, and then practically you're giving way to icy bodies at that point. So the icy body will still have a rocky core. So all we're basically saying with this is, rather than being a traditional rocky planet, that rocky planet becomes the core of an icy body instead. So whether or not a planet is an Earth-like will depend on not just its temperature, but also the atmospheric density and the atmospheric composition as well. Right now, anything that can support liquid water and has an atmosphere is considered to be an Earth-like, and that's a little bit too vague. We need to tighten that a little bit. So gas giants, again, the chance of a gas giant increases the further you get from the star, and it peaks around about the frost line, and then that drops down to make way for ice giants, and you can see that there's a crossover where gas giants become ice giants. And then we have our icy bodies, which begin from the frost line again. So the further you get from the frost line, the greater the frequency of icy bodies occurs. Now, these curves are based on scientific data and papers that I've been perusing, but I'm going to be running this past the sort of collection of PhD types that we've got on our server, to make sure that we have sound, accurate science basing all of this, or backing all of this up. Yes, there can be hot Jupiters. So round about here, you can see that the lowest percentage chance for a gas giant is 20%. So there's a 20% chance that there will be a gas giant literally right up against the Roche limit, and that would very much be a hot Jupiter. What's that, 1 in 5? Yeah, 1 in 5, 20%. Looking at exoplanet distribution, it tends to be fairly linear, so you get quite a steady distribution of gas giants across all distances in a planetary system. But the issue is that the data we have is skewed by the fact that most of the exoplanets that we found happen to be large, either super-Earths or gas giants, because our detection methods aren't really fine-tuned for finding really small planets. So there's only so far you can go with real-world exoplanet data, because that data is skewed towards the heavier planets. But I was reading another interesting paper that was saying that because of the magnetic field in a protoplanetary disk, again, the dense matter, i.e. iron, tends to congregate towards the inner edge of the protoplanetary disk, and that magnetic field dissipates as you go out towards the outside of the disk. So again, the density of the planets, the density of the planetary cores, the mass fraction of the planetary cores all tends to be higher the closer to the star you get, because that's where all the heavy dense material is. But yeah, so that's basically how we're deciding what base planets to make. And of course, these are just the base type of planet. So a gas giant can be a full spectrum of different types of gas giants, and a rocky planet, in air quotes, can be everything from like Mercury to Earth. So now that we've defined our planet type, we need to define our planet mass. This is a fairly simple equation. The hydrostatic equilibrium is the mass at which a planet can sphericalize itself. So lower than this mass, the amount of matter will not be able to pull itself into a sphere shape. So I'm using that as the lower limit for the smallest dwarf planets that we can have. Anything lower than that mass, and they're essentially an asteroid. We have a 1% chance that any rocky bodies will be a dwarf body. So essentially you're looking at a Pluto/Moon sized object rather than a full planet. 99% of the time it's going to be a mass, anything from the mass of the Moon all the way up to 2 times Earth's mass, at which point you're starting to get into gas giant territory. And that's that crossover where you have a terrestrial world, i.e. a rocky world, and that transition into what's essentially a water world. before it becomes a gas giant. You've got that kind of middle ground. And then gas giants goes everything up to 13 Jupiter masses, beyond which it becomes a Y-class star. And you've got 2 times Earth up to about half the mass of Jupiter for the ice giants. And then dwarf planets, which are the icy bodies. That's fairly straightforward. So now that we know where the planet is, what the base type of the planet is, and we've derived how much mass that planet has, we then get into the slightly more complicated area of defining the actual density of the matter that makes up the planet. So you can see here again we're working on the assumption that the heavier elements are on the inner edge of the protoplanetary disk. I've done a lot of spreadsheeting and a lot of testing of the various values here. And essentially what we're doing is we're taking the masses of known materials. So for example, iron here is 7.8 grams per meter cubed. And that's our upper limit for a planetary core as an uncompressed value. Obviously, if it was pure iron, which is, the heaviest it would be likely to be, that's pure iron uncompressed. And then, depending on the mass of the planet, we then have to compress that value. So what we're doing is we're going from essentially the mass of the moon up to the mass of 2 Earths, and then increasing the density of the core accordingly. And the same there for the mantle as well. So essentially the more mass you add to the planet, yes, that planet gets bigger, but at the same time it gets smaller because it becomes more compressed. And then for the crust, we just throw some random numbers at it because it doesn't really matter at that point. Yep, we will get to atmospheres in a moment. So that's the data for the rocky planet, and we do less work for icy bodies because they don't have to worry quite so much about compression because they're all kind of dwarf planets, so just the materials as is sufficient. So again, for the core, like with Pluto, Pluto's got like 70% of its volume is its core, and that's just a rocky core. And we're going with essentially like basalt, just rock at that point. So that's likely to be the maximum that the density would be. 3,100, so that's 3.1 grams per meter cubed is the typical density of lava. So if we assume a molten core for Pluto, then essentially that's what that density would be. And then you've got 1100, which is, I think that was liquid oxygen. So I can't remember whether it's oxygen or nitrogen, but probably oxygen. So that's the density of that. Density of liquid water, of course, is 1 gram per meter cubed, and ice is 0.9 grams per meter cubed. So the crust of an icy body is essentially ice, so that we know what the density of that material is. Then, once we know the density of the layers, we can then look at the mass fraction for the core. Again, this is where it starts to get more complicated. So we know typically the core mass fraction of a terrestrial world will decrease the further from the star you get, because again the amount of high density material, i.e. iron, in the protoplanetary disk gets less and less the further out into the system you go. So we're taking the temperature, the equilibrium temperature, to define our distances. So rather than using a distance in kilometers, we're just using the temperature value, because that scales depending on whatever star you're looking at. And then we are picking our mass fraction based on that. So towards the the center of by the star, by the Roche limit, half of the planet's mass is its core, and then out towards the frost line, only about 20% of the planet's mass is its core, and that's true for Mars. So Mars has about 20 to 25% of its mass taken up by its core, and then at the opposite end of the spectrum you have Mercury, which is more like 70%, but then Mercury is a bit of an oddball, and the current running theory is that Mercury's massive core is because its mantle got stripped away by a collision at some point in the past. So I'm not using Mercury's data as our upper limit, because it's a bit of, it's an edge case, and edge cases haven't really been taken into account with this yet, and that is something that I'll roll into it further down the line. So everything I'm building here as part of the core system is normality in the galaxy. So this is the typical star system that you'll encounter. What we need to add to this is things like Mercury, where the core size is far beyond what it should be for its position and for its size, and that's because an event happened to that planet in the past. So what I'll do is I'll add a separate layer where we can flip a coin and decide whether or not the planet that's forming is going to have had something happen to it, and then we can roll that into the description as well, and just point out on the Census UI that this planet is weird because. So it just gives that little bit of extra something to go out and explore and find those edge cases. So we calculate our mass fractions, and then with that we're able to define the actual mass in kilograms of each layer of the planet. So you can see we're going into quite a lot of depth with this. Next, we need to sort out the radius and the volume, which, that's not what that is, which is what I need to be doing in a moment. That'll be the first thing I work on. The old code for that is kind of nonsensical, so that can get dumped. And again, the old density code that we had before, the new version is a lot more refined and a lot more accurate, so I'll probably delete those at some point. And at that point we can then move on to just calculating the gravity, which should be fairly simple. We know our mass, we know our radius, so we should be able to use the gravitational constant to generate our gravity value. Should be quite straightforward. This should already be correct, but I will go through it and double check. And then we can do our atmospheres. So right now, atmospheres are literally a random yes or no. There's an atmosphere. Obviously gas giants and ice giants have always got atmospheres, and icy bodies, at the moment it's set to never give them an atmosphere, but in reality they kind of all do. Even icy moons have atmospheres. They're very tenuous, but they do have them, so I'll do something with that. And we also need to go into a lot more detail here about the actual atmospheric composition as well. So beyond its density, and that's another value that we're going to have to calculate. So we'll calculate the height of the atmosphere and the gravity of the planet, and thus the density of the atmosphere, and that will have a very direct impact on the life that gets generated in that world, if there's life. And then we can do our surface temperature based on greenhouse effects from the atmosphere, and then adding it all together where we choose our final planet type. So we haven't actually decided, for example, whether or not it's an Earth-like yet until we kind of get to this point. That's the last thing we do. And then all of that just kind of gets added together and built into a planet struct object. And then that's what gets read by the game to spawn the planet in the game. Phew. Okay, so I know I whizzed through that really quickly, but that's essentially how we are building planets within the game currently. And we will, like with everything else, we will just iterate and iterate on this to add more complexity over time and more detail and more interesting edge cases and that sort of thing. Right, so assuming that everyone is still awake after that, let's go and have a look at doing the volume. That is no longer correct, although I think what I'll do is I'll get rid of that for now, replace that with the code that I did earlier. So I have a Google Sheet. Apologise for blinding everyone. This is a mess, but this is basically my scratch pad, and this is where I scribble down all of the math that I'm doing before I implement it into the game. Somewhere down here I was doing radius calculations. Oh yeah, here. So we're basically taking the mass of the planet, calculating the volume, and calculating the radius from that, based on the core mass fraction. So I need to translate all of this now into the game, which would be this. So I know that it works in a spreadsheet, so I shall pop that in there. I'll just remind myself of what those values were. So that was core mass and core density, or more specifically layer mass and layer density. And then we're timesing it by 0.001 to make it kilometers because it's meters by default. So that's our math. So we need, first of all, the core mass in kilograms. I might condense this into a macro as well, just to make it a bit more efficient. And then we're dividing this by... It's 4 times pi. Multiply that by the layer density. So it's core density, that one. And then we're raising all of that. No, wrong type of power. I could just put right 0333333, but I'll do it properly so we have a more granular value. The remaining rooms will be frameworked for the demo, so they won't have actual wall panels and proper lighting and floors, but the actual metal framework should be there. So you should be able to at least wander around in new areas with a torch. so 3 times the core mass divided by 4 times pi times the density of the core, raise that to the power of 1 divided by 3, and then times by 0.001 to turn it into kilometers. Right, so if I collapse that to a macro, and then we'll call this, what are we even working out? Calculate radius from mass density. That'll do. Radius no, that's not what I wanted to do, was it? Density in kilograms per meter cubed. And the mass just in plain old kilograms. There, and that needs to be radius in kilometers. Actually, I don't think we do need an execute on there, do we? We can just do that. Yeah, that'll do. Yeah, so I am planning on putting a demo update out as soon as possible. I just need to get all this stuff finished first, because the idea for this particular patch cycle is that we've at least got the beginnings of alien life in the galaxy, and all the stuff I'm doing with the planets here and refining that is the foundation work that needs to be done so that we can start generating life on these planets. It's a bit of a chicken and egg scenario, because we can't really start generating plant life and flora and fauna without knowing the density of the atmosphere and that sort of thing. I mean, we could, but it would be wrong. Do we have a core radius already? Yes, we do. Do I do the volume separate? I don't think I need to, do I? So just do stick in a sequence and do it that way. Core, mantle, the mantle mass. mantle density and mantle radius. Crust mass, crust density, and crust radius. Right, so that should give us accurate radiuses for each of the layers of the planet. In the future, we might split these even more and have like inner core, outer core, and that sort of thing. But for now, I think just core, mantle, and crust is sufficient. And that gives us enough data that we can actually draw a 3D model of the planet with like a wedge cut out of it, so you can see the insides, which I am very excited about. And then finally, we need to actual planet radius. So we just take core, mantle, crust, and quite simply, we simply add them together, and that gives us our planet radius. Okay. Trying to make sure I haven't forgotten anything. Don't think so. I suppose the overall volume would be useful at that point. So why am I timesing it by a lot? I believe that's right. Mass divided by density is volume. Just double check that. Is correct. So, do we have everything we need now? So we got radius in kilometers, we've got I will have to double check that we've got the actual Is that giving us meters or kilometers? Pretty sure that's probably meters. Yeah, because that's meters cubed. So are we dividing that by 1,000? Yeah, I'm pretty sure that's going to give us a value in meters, so we need to times it by 0.001 to convert it to kilometers, and that gives us our volume in kilometers cubed. It looks right. We'll see if it's right in a minute when I actually run it. Right, so everything that was doing, we have now replaced, so that can go away. I'm pretty sure all of this has been replaced now. So that can go away as well. Right then, so next is gravity. Googling the gravitational constant. So 6.67430 times 10 to the power minus 11. Yep, seems to work. Oh, am I missing something? So that's times mass cubed. Ah, thanks, Libertas. Of course, I'm thinking of a straight line, aren't I? So that would be 1 to the power... No. Oh, 10 to the power 9, isn't it? So it's that times... 1 billion. Yeah. I'll be the first to admit, maths isn't my strong point. So it's kind of hilarious that I have to do so much maths on a daily basis. Yeah, it's funny because when I tell people I do programming for a living, they say things like, oh, you must be really good at maths. It's like, actually, no. You sure it's -9? Because 10 to the power 9 is a billion. And 1,000 times 1,000 times 1,000 is a billion. Yeah, well, that is right. It's 10 to the power 9. Oh, of course, yeah. So I'd need to divide it by it, not multiply it by it. Yeah, so if I was to divide that by that, then that should make sense. Yeah, that works. Typically, computationally, it takes more effort on the CPU to divide than it does to multiply. But for a one-off task like this, it's kind of negligible. Are we all happy with this? I think we're happy with this, aren't we? So on this one then, we are... So we take the gravitational constant, we multiply that by the mass in kilograms, we divide that by the radius in meters times by itself, and that should give us our meters per second per second. I believe this is correct. If you Google the gravitational constant, it's more complicated than this, but I believe that's actually the correct way of doing it. Let me just double check. going to quickly double check this a minute. So, hang on. Apologies for the blinding again. I think I did actually already calculate it on here, then kind of deleted a bunch of the stuff that I was doing, typically. So we want 6.6743 multiplied by 10 to the power minus 11, which gives us a tiny number, I believe. Then we multiply that by, let's go that, except we want that equals that divided by 2. That should give us so that's Earth's mass. That times that. Yeah. And we're going to divide that by the radius of Earth, which is what, 6,000 and something. 6371 equals 6371 times 1,000. Let's make it into meters. Times itself. I suppose that's power 2. So that was, so it equals that divided by that. Should give us our value for G, which is almost the same as that. Yeah, so what we're doing here does give us the approximate value for Earth's gravity, given that in kilograms. Not quite sure why it's not precisely correct, but I'd say it's close enough, because it's probably, obviously that mass value would change this, so given a more accurate mass, I'm sure that would be more accurate too. Okay, so we know that the gravity calculation is correct. Tick. Okay, next. I think testing purposes, I'm going to leave this as is. except we're going to give icy bodies an atmosphere, and then we're going to make that atmosphere really, really tight. Probably even less than that, to be honest, 0.25. We'll see how that looks. Okay, so temperature. It's a bit of a mess from before. We can be more precise with our bond albedo, because we now know what planet type we are using. So why don't we? Let's get rid of that. Get our base planet type and we will switch on that. Right, so if we're going with a rocky planet, then we know our star temperature, we know the planet's distance. So the albedo of our rocky planet is going to be, if we use Earth as an approximation, it's about 0.15 or something like that, 0.12. No, it's much higher than that, 0.3. So the moon's albedo is 0.12. Mars is 0.4. Earth is 0.31. And Mercury is 0.15. Right, if we go with 0.3, let's use Earth's for now. I need to find a better way of calculating this albedo. I suppose, thinking of it, if the planet has an atmosphere, then that value is going to be different. So, yeah, let's do that. So, let's run a select with this. So if it does have an atmosphere, we'll go with 0.3 to match Earth. If it doesn't, we'll go with 0.12. That kind of matches Mercury and the Moon. So that's the difference between a pure rocky body and something like Earth with an atmosphere. Just to make that, that equilibrium temperature as precise as possible. So then we'd set our temperature, and no output is needed. The bond albedo represents the amount of light reflected back. So a bond albedo of 1 would be a mirror, and a bond albedo of 0 would be like the blackest black that absorbs all light. And the highest albedo is actually Venus. Yeah, Venus has an albedo of 0.7, so it reflects 70% of the light that hits it. By contrast, the albedo of snow is 0.5 to 0.8, so it's Venus is practically fresh fallen snow in terms of its brightness, which is crazy. That's why it's so bright in the sky at night. Yeah, super chats. I need to send loads and loads of paperwork across to. It's not Google. It's the AdSense thing. They want a copy of my passport and driving license and various other bits and pieces. It's a crazy amount of ID just to enable super chats, but I will get around to it at some point. As Claire says, I'm always so busy working I never get around to the paperwork side of things. Okay, so gas giants and ice giants. Shouldn't really need to calculate anything for these. We shall go just check the gas giants. Let's see what their albedos are. Jupiter is 0.5. Saturn is 0.24. Okay. Venus is 0.48 and Neptune is 0.44. So if we go with, let's go with 0.45, that's kind of a happy average for gas giants. And then icy bodies are obviously going to have quite a high albedo, unless of course they're covered in tholins, in which case they won't. So Pluto's albedo is 0.4. It's an interesting one because Pluto's surface is covered in tholins, which is that brown tinted stuff. The albedo changes depending on where on the planet you look. Average wise, it's going to be slightly higher than the gas giants because obviously it's ices. I think I might just go with just 0.5. Sort of exactly average. So obviously the albedos that we're using are rough, they're an estimate. Over time I need to find a better way of sort of refining this value. Again, it's one of those chicken and egg scenarios where, at this point, we've defined very little of the planet's structure. We know how big it is, we know whether or not it has an atmosphere, but we know nothing about the surface conditions. So it's difficult to define an albedo when you don't know yet what the surface conditions look like. And you can't really define those surface conditions until you've jumped through some of the other hoops. So once we've done it all, I'll have a look at the order of things and see whether kind of swapping the order around makes some things easier to calculate. So obviously this is literally just the equilibrium temperature. It's not taking into account any kind of greenhouse effect from atmospheres. Was I doing that before? Sure I was. What we'll do is if we stick a sequence node in there, do that first, and then what we'll do is we'll once again redefine the planet temperature. So we're constantly updating this variable and refining the temperature as we go. So we need the temperature of the planet. And we shall multiply that by a range of values. So this is essentially going to be the greenhouse effect, which means the atmosphere thickness is going to need some randomness applied to it in a moment. But if we go from 0 to 4, maybe make it 5 really thick atmospheres, and then maybe 0.01 is the minimum. Just the easiest way to work this out, if we look at Earth's equilibrium temperature, so Earth is actually 255 Kelvin, which is minus 18 C, or minus 1 Fahrenheit if you're that way inclined. So the effect of the atmosphere increases that from 255 to 288, which is an increase of what? So 255 it's about 10%. 255 to 12.2. Yeah, so if we put that as 1.25, so for very, very little atmospheres, we don't want to really change the equilibrium temperature at all. For a very thick atmosphere, we want to increase that significantly. That said, what is the equilibrium temperature of Venus? Because obviously Venus atmosphere has a crazy effect on its temperature. Wow, yeah, so the equilibrium temperature of Venus is 260K. So without an atmosphere, that's how hot it would be. With its atmosphere, it's 740K, which is absolutely ludicrous. Which I suppose is runaway greenhouse effect for you. So I think for now, we'll leave it at this, which would, it's enough to satisfy an Earth-like. So an Earth-like would have an atmosphere density of around about 4, and that's not a unit of measurement in any way. That's just 400% capacity, I think, just in the shader. So an Earth-like atmosphere would increase Earth's temperature enough to match reality. This doesn't take into account something like Venus, so that's something that we have to roll in later down the line. Yeah, that's a fair point, Ian, as well. The actual composition of the atmosphere also makes a difference, not just its density. So there's a few refinements which need to happen here to make it so that an Earth-like world is truly an Earth-like world in every way it possibly could be. And I think within the game we'll start referring to it as an Earth analog if it is like exactly like Earth. So similar radius, similar atmosphere, oxygen, nitrogen atmosphere, that sort of thing. So it is truly an Earth analog. And then we'll have some other definition for atmospheric worlds, which are similar to Earth, but with a different atmospheric composition. Yeah. Hey Martin, yeah, so the gravity is going to be... It's not going to be Kerbal level physics, for sure, but we do want orbits implemented within the game in a way that doesn't require anything Kerbal-like to achieve. So the current thinking is that we'll draw a spline or a rail around the planet based on your current altitude and position above the equator, and it will automatically place you in a circular orbit and move you along that rail at the appropriate speed for that circular orbit, and that will apply to anything else like stations or other ships and things around the planet. So if you exit FTL next to a station, your rail around the planet will be practically the same as the stations, and thus you will be orbiting together around the planet next to each other. The alternative to that is if you weren't doing that, then the moment you exit FTL, that station is moving at say 7 to 10 kilometers per second, and it would just be gone in the blink of an eye, and then you wouldn't be anywhere near it anymore. So we really need to put some helper functions in there to make the game, practically playable, without having to resort to actually matching orbits and that sort of thing. Yeah, and once we start doing the exobiology, definitely atmospheric composition is going to play a big part in that. Also, the type of surface fluids that are on the world, it might not be an H2O based ocean world, it could be some other fluid. So something we need to do here is we need to randomize this a bit. So gas giants are always going to have a thick atmosphere, that kind of goes without saying. We'll stick some randomness in for icy bodies. So we get our random stream. So we want a random float in range from the stream. And we'll just do from 1 to 5, and that is our random atmosphere. And we'll do a similar thing from here. We will do 0.01 and maybe 0.25, something like that. So when it comes to rocky planets, it's just a straight 50-50 dice roll as to whether or not it has an atmosphere. Although, that said, we do need to take proximity to the star into account at some point. So if the planet's too close, then the atmosphere, of course, needs to be stripped. And I just need to look at the math as to how close is too close. For now, it can just be a 50-50 dice roll. and then we'll just do a dice roll on how thick the atmosphere is. So for it to be an Earth-like, the atmosphere is going to have to be thick enough, so around about 4. There are, I would say, too many Earth-likes in the game right now, and as we refine these numbers, I think the amount of Earth-likes is probably going to decrease quite significantly, because you really need to hit the sweet spot with all the generation. Yeah, for sure. Is that all the way over there? Evening, Jack. Welcome to the stream. All of the stars, apart from the ones we're backfilling, within a 2,000 light year radius of Earth are real stars from the Gaia catalogue. Everything beyond 2,000 light years is procedural. That kind of has to be the case, because even a 2,000 light year radius is already 2.5 gig of SQL database. And it's 18.2 million objects, which is crazy, and that's just within 2,000 light years. Yeah, we'll definitely have things like standard orbit, and various, what you'd expect parking orbits to be. Right, so now that we have all of this information, we can determine our final planet type. Word on there. Yep. Alright, so this was messy before, so I think we will definitely clean this up. Right, so we have our 4 base types, and now we need to refine those base types into actual proper final planet types. Yeah, that would be so cool. I mean, one of the reasons that I want to go into such crazy detail with this is because of the Drake equation. And it's that if we are modeling this galaxy and we are getting the astrophysics so correct as to be analogous with reality, if our simulated galaxy is absolutely filled with Earth-like worlds, using real astrophysics and real numbers based on real data, then surely, by extension, the real Milky Way should have a similar number, ballpark, of Earth-like worlds. I mean, if we've got the math correct, then that should be the case. And that's really exciting for me. Right, so previously we were literally just using temperature to define planet type, and we need to go into more depth this time around. So we need our temperature for one, definitely, and we also need the mass. Where's the planet mass? Planetary core temperature is not something that's modelled yet. But that is definitely something to add to the list. Of course, core temperature is also a fairly vital data point, because planets like Pluto, unbelievably, do have a liquid ocean underneath their crust. And that's because Pluto's core is about 1,000 Kelvin. And in fact, I think most, if not all, of the icy bodies in the solar system do have water oceans underneath their icy crust. For me, the equation's quite simple. It's if we go down the assumption that the presence of tholins is a precursor to complex life. Tholins are organic compounds, so they're the first step on the ladder to an actual, organic. There's lots and lots of horns and screaming going on in our street, so I can only assume that England just scored. So if the presence of tholins is the precursor to complex life, then our solar system is filled with tholins. I mean, like Pluto is absolutely covered in tholins. That's why it's so brown. So if tholins are all over the solar system, and the presence of tholins is fairly ubiquitous across the whole galaxy, then that means the precursor to organic life exists in every star system, because tholins are a natural side effect of solar radiation. So, to me, that means that life should be abundant, because the recipe for life is there. But let's see how that comes out in the math, because the presence of tholins is going to be also the thing I'm using within the game to determine whether or not that sort of ambiogenesis is there. Yes, Voorhees, I am everywhere. Night Owl, yeah, so the galaxy is known as the Milky Way, and Sol is the name of our star system. Our sun is called Sol, as in solar energy. That's where solar comes from. It's probably Latin. Right, let's get our head around what we're doing here. So, I reckon all that's trash, so I'm just going to delete it and start again. If we start with the mass first, perhaps, then so we need final planet type. We have a whole list of things we can choose from. Obviously not stars. Ah, thank you, Claire. I'm just getting my head around whether or not we needed lava dwarf planets, so I don't suppose we do, really. We are differentiating between metallic and silicate lava worlds, but to be honest with you, that's kind of irrelevant because all lava worlds are going to be inherently metallic because of their position in the system. The only reason a silicate lava planet would exist if it migrated to its position. I think I may just go with metallic only for now. Then we'll have a look at those. Terrestrial worlds, however, they can be more metallic. Or, that said, I think I'd rather distinguish the metallicity of a planet with its data rather than with its planet type. So I think, yeah, lava planet as the base, and then terrestrial planet as the base. Although, see, the term terrestrial planet is kind of the recognized term for a non-gas giant, but you know, in gaming terms, a terrestrial planet is often confused with the term Earth-like. So if you see a list of terrestrial planets, it looks like it's just a list of Earth-likes, which is not the case, because terrestrial just means rocky. And I'm wondering whether or not we should just start referring to them as rocky planets instead. I'll have a think on that. Hey Mike, thanks for joining. Because we can also differentiate super Earths and mini Earths as well, but technically a super Earth is anything larger than Earth, but do we need to at this point is the question. I think perhaps not. So let's just go with what we've got for now, and then we can iterate after. Right, so we need to define some temperature regions, don't we? So, if the planet temperature is higher than the melting point of rock. So what's... So about 1500 Kelvin is the temperature of lava. So you would expect if the temperature was this, if the planet was this hot, it would just be lava, because that is the temperature at which rock melts. I suppose another way to look at this would be basalt melting point. Yeah, so basalt is liquid at 1400 Kelvin. What about granite? So 1500 for granite. Yeah, igneous makes sense. Although I think we'll leave it as terrestrial, because that's the term NASA uses, and it would be nice to use kind of commonly accepted terms within the scientific community. Water worlds we will get to momentarily. I think a low mass warm gas giant, I think at that point we'll look at that as being a water world, or a high mass terrestrial world that's warm. Yeah, exactly. No need to reinvent the wheel. Right, so we're going to need a bit of a cascading true or false branch here. So the temperature over 1500, we're going to make a metallic lava planet. That's an easy one, because the temperature of the surface is hotter than it takes to melt granite, therefore it is a lava planet. Nice and simple. So if it's not hotter than that, range, in range, there we go. Okay, so if the range, now this is an interesting one, because like at what temperature range do we classify an Earth like? Now obviously the temperature of Earth is around about 15 degrees C, I think, on average, which obviously is enough to melt water. But do we do it the full temperature range of liquid water? So 273 Kelvin is the melting point of ice, and obviously boiling point is 290. Quite a bit hotter than that. 373. So 50 degrees C is 323 Kelvin. One would assume that a surface temperature average of 50 degrees C would be incompatible with an Earth-like. Martin, yes, surface locations will be explorable. So the idea is you'll be able to take a shuttle down to a planet's surface and explore on foot. In terms of gameplay, the general idea is all built around exploration. So it's about conducting science on the flora and fauna that's there, and discovering things which can help your ship in various ways. All of the upgrade paths for the ship and crew are going to be through exploration. So the more science you perform, the more discoveries you make, and the more you can upgrade your ship. And throughout the galaxy there will be star systems and places which are kind of beyond the abilities of your ship and crew. So upgrading and refining and making everything better aboard your ship grants you access to those areas. And we intend for the end game content, the biggest bads in the game, to be in places where you're not even going to be able to get to those locations without an amount of upgrading. But we'll be refining those things as we start working on the gameplay loops in earnest. Yeah, so going by as an average, just Google it a sec. So Earth average temperature. Yeah, 15 degrees C is the average temperature on Earth. So if we take the average temperature as our cutoff point for an Earth-like, so that would be 0 C to 50 C. That's the temperature range in which we would consider something an Earth-like. Although 0 C is perhaps too high. So I'm just thinking, just because there's ice across the surface, like if the average temperature of Earth was 0 degrees C, would the oceans freeze? And I think they probably wouldn't. Yeah, so a planet like Hoth, it's a good example. It's got a breathable atmosphere, it's just really, really cold, but life does exist there. So I guess the question is, how cold is too cold before being an Earth-like is no longer viable? Yeah, exactly that. I suppose another way to look at it is that we're talking like Earth analog here. So this isn't necessarily the definition as to whether or not life exists here. It's whether or not we're classing it as an Earth analog. So I think for that purpose, perhaps 0 to 50 is probably a decent enough range. I mean, the average temperature on Mars is minus 63 C, that is. Which is 293, or highs of 293 Kelvin. The average temperature in Greenland is 5.6 C. Average temperature in Antarctica is minus 60. Yeah, I think minus 10. I think that's, I mean, we get minus 10 in the UK rarely, and you know, you can still walk around in it quite happily. So I know other countries get a lot worse than that. Why don't we do 260? Round it to a nice round number. So 260 Kelvin is minus 13 degrees C, and 320 B, that would be 46. Yeah, that's so that is minus 13 to 46 degrees C, and that gives us our Earth analog. Yeah, so when it comes to extremophiles and that sort of thing, they will exist and be thriving on non-Earth-like worlds. So I think the term Earth-like, I think I'm going to change that to Earth analog, so that we kind of make the definite definition. We're not talking about whether or not life can survive there. We're talking about, is it suitable for human habitation? Yeah, I've never been anywhere that's been like properly cold. I'd certainly love to give it a try one day. Well, I just thought of a point. So there's actually, we also need to think about the atmosphere. Yeah, so if the atmosphere is within the right kind of range, we'll also use that as a deciding factor. Otherwise, we need to do resonance sphere. So if it has an atmosphere, it is a oh, that's interesting. Why haven't I got atmospheric terrestrial planet here? Interesting. Minus 39 Fahrenheit is right. Could look onto a worse web page. Calculator is minus 39, so pretty much the same value. I think that does class as properly cold. So I need to refine this this enum a little bit, because I don't think that's quite what we want. So, basic lava planet. So we've got terrestrial planets, and we'll have atmospheric terrestrial planets, Earth analog, the gas dwarf is technically a mini Neptune, and I'm going to remove that for now. It's a kind of a meaningless classification, really, because referring to something as a mini Neptune just means it's smaller than Neptune, which isn't particularly useful. So you've got icy bodies. planet kind of needs to go there. Just organising the list a little bit. Right, so we've got all of our star types and black holes. And we've got lava planets, dwarf planets, terrestrial planets, atmospheric terrestrial planets, our Earth analog, water worlds, gas giant types, ice giants, icy bodies, asteroids, comets, and city planets. So the city planet is perhaps... Yeah, things like pulsars, T-Tauris, or neutron stars. They'll be coming, and I'll add those like when we get to them. Although now that you've mentioned it, why don't I just do it now? So I won't include pulsars because pulsars are essentially just neutron stars. They're just neutron stars that happen to be facing us. Yeah, city planet is going to be literally, as the name would suggest, like a coruscant. And I need to make a proper material for that so it looks like a city planet from orbit. Neutron stars, you got white dwarf. Yeah, you make a good point about gravity, actually, for Earth analog. Yes, the gravity should be within a certain ballpark of Earth. I guess the question then becomes, how high is too high? Yeah, LT and Y class of the brown dwarfs. Yeah, Berry Center will be something I start thinking about when we have multi-star systems. I imagine the first thing we'll add is like classic binaries where you just have a pair of stars orbiting a set Berry Center in the center of the system. Where it starts to get complicated is where those two stars are separated by a great distance and each of them have their own set of orbiting planets. Or you have multiples thereof, where you've got binaries orbiting binaries and all sorts of other shenanigans going on. What have I missed? We've got neutron stars, white dwarfs, T-Tauri. I'm sure I've missed one from the list there. Oh, Wolf Riot, that was the other one, wasn't it? I'll actually pop these at the bottom here underneath black holes organisationally. I'm going to remove City Planet as a planet type in favour of having it as a planet outcome. So it would just be an Earth analog that's very, very high tech, essentially. Right, so we've got our main sequence, we've got our brown dwarfs, we've got specialty stars, I suppose a giant star in there as well. Yeah, we should be okay distance-wise because all of the planet types are done the moment you pass within half a light year of the star, or you click on the sensors. It generates all that data at that point. So the fact that it's a city planet would already be known the moment you enter the system. It's a good question, Cloud. I think I'll have to build it and see, and then we'll find out whether there's an issue with it or not. I have a feeling a lot of different assets are referencing this enum, so rather than saving all, I'm simply going to quit the engine without saving any of those, because I'd have to go in and sort all of that out otherwise. So we won't save those, and then we will reload the engine. I know I don't have any space. At some point I will order some new computer parts. Yes, the cinema will have very typical cinema seating. Okay, that's neater. I might further reduce this list because, yeah, a lot of the definitions of these are kind of defined later anyway. I'll leave it like that for now, but there's definitely room for improvement there. Yeah, we're definitely using distance as our deciding factor when it comes to the amount of detail you get from the sensor scans. So from outside of a star system, all you will be able to see is the base planet types. So you'll see whether or not it's a terrestrial planet or a gas giant, and that's all you'll know. You might see whether it has an atmosphere, but that's about it. You won't be able to determine whether or not that is an Earth analog until you're within half a light year of the star, i.e. you're within its 1 light year cube. And there's a very technical reason for that. That's simply because we cannot generate the data until you're within the cube. Otherwise, we'd have to be generating the data for every single star in a sector, which is a mental amount of data. So we physically cannot generate that data beyond the cube that the star exists in. Whether or not there's actual life on that planet, you will not be able to determine until you are within visual range, and then can direct the high gain sensors at the planet's surface. So it's very much a stepped thing. If you really truly want to see whether there's life on a world, you have to go to within visual range of that world. Yeah, sensor range is going to determine kind of what shows up on the sensors in terms of objects within range. If your sensors are broken in some way or underpowered, then like the list of stars in range would be a lot shorter than it ordinarily would be. And I guess as well, when you're scanning things on the other side of the galaxy, those things will become out of range if your sensors are broken. So yeah, we wanted to do gravity as well, didn't we? So what is we did maybe 20% each way. So if we were to do 20% either way of Earth, that's 7.8 meters per second up to 11.7. What's the moon's gravity out of interest? So the moon is 1.6. Probe range will be visual. Declan, yeah, the GPS is a passive system. So that's the spinny dish on top of the roof. And that's literally just pinpointing the location of the ship in the galaxy. And that's all it does. The sensors basically read the data that's generated for the sector that you're in. So the galaxy is split into 100 light-year cubes, and each one of those 100 light-year cubes has all of the data that's needed generated and stored in memory. What the sensors are doing is they're accessing that data. So say you've got 20 planets that have an actual civilization on them with FTL ships of their own flying around. That's the sort of thing that will be available on the sensors because you're within range of those objects. As you pass beyond that 100 light-year cube, those things are no longer being rendered. Although specifically it would be more like 150 light-years because it's a 3x3x3 grid of sectors around the ship. So you have to pass beyond 150 light-years before a sector unloads. Zelaf, yeah, definitely. The more broken things get, the more nonsensical the data readout should be, for sure. It would be great to have the sensors broken to the point where the ship literally doesn't know where it is. If someone shoots off your GPS dish, then you're blind as to where you are in the galaxy, which I think is a nice dynamic. So you've got to fix the GPS before you can even navigate anywhere. Thank you, Wilbur. So I'm thinking, in terms of gravity for an Earth analog, we can probably cope with less gravity than we can more. So I would think that the upper range would probably be like 12. So that's 25% more gravity that's on Earth, which would be around about 12 meters per second. So let's go with that. So that would be 12.27. 12.27? 27, yeah. So that would be our upper limit. But in terms of the lower limit, would the gravity of the moon, for example, be too low to be considered an Earth analog? I mean, you can definitely still walk around quite happily. What Mars's gravity is. Yeah, so the gravity on Mars is 3.71. That's less than a half. That be so that's more than a third. Yeah, it's about 40% of Earth. So yeah, I reckon we'll go with Mars. It's tempting to use the moon, but the moon is perhaps a little too low to be considered, an Earth analog, technically. So that would be 3.7. Don't know. That's just basically me ballparking some figures. Let me know what you think. I know I'd much rather less gravity than more. Yeah, so an Earth analog, at least in terms of what we're building here, is a planet where you could literally land your spacecraft, get out, build a cabin and live. See, on that note, I'm wondering whether minus 13 is perhaps a little bit extreme. $270 minus 3. Again, we're talking about the global average, not specific points at the equator or whatever. So if I just chop 10 Kelvin off of both of those values, so obviously at the equator it would be hotter than that, and at the poles it would be colder than that. But that should give us a decently habitable temperate region. I imagine the debate on what constitutes as habitable in terms of temperature range or Earth-like could probably go on for some time. Right, I think that's it for Rocky Worlds, actually. So we've got our lava planets, our Earth analog, atmospheric terrestrial, and just non-atmospheric terrestrial. So those are done. Let's give them their proper name. Right, so there's terrestrial worlds. So ice giants should be fairly straightforward, really. Gas giants are going to require a temperature range, so let's do them next. Right, so there is a classification of gas giants, and I cannot remember the name of the scale off the top of my head. I want to say like Swarovski, something like that. Gas giant classification. Sadarsky, there we go. So I think the Sadarsky scale for gas giants is kind of debated, although it is used in quite a few things. Okay, so if we go hottest to coolest, right, so if the temperature's over 1400 Kelvin, we are a class 5 gas giant. Over 900, we are a class 4. Over 350, then we are a class 3. So class 2 are too warm to form ammonia clouds. Instead, the clouds are made up of water vapor. These characteristics are expected for planets with temperatures below around 250 Kelvin. And in class 1, these planets are found in the outer regions of the planetary system. They exist at temperatures less than 150. So if we do 250 for class 2s, otherwise it's a class 1. Clean it up a little bit. Okay, that should be all we need for the gas giants. Doesn't quite seem like enough, but I think that's pretty much it. 5, 4, 3, 2, 1, with some temperature ranges. so next is ice giants, and to be honest with you, I don't think there's much to distinguish those really, so it's just literally, I'm an ice giant. I guess icy bodies are the same, aren't they? There isn't a range of those, so... Okay, so we're missing water worlds, and I'm really... Water world kind of needs to come off here. If the mass is sufficient, because they're quite a high mass planet. Right now, whether or not the planet has rings is done at kind of a spawn time. So we take the seed for that world and determine whether or not it has rings. And it's just literally a flip of a coin, does it have rings or not? When we add moons, those moons will become rings if they are spawned within the Roche limit of the planet. So they'll start to make more sense, essentially. So I'm just thinking with this, there are kind of two different types of water world. You've got the water world as depicted on TV, which is a planet with little to no islands. And I think I will base that off of the Earth analog. So when we come to generate the actual continents and things, if there aren't any, then essentially that's practically a water world in the traditional sense. However, a true water world is more of a gas giant. So in that regard, I think I'm going to stick it in here if the temperature and the mass range are within the right bounds. Yeah, so if I'm gonna squeeze them in here. I'm going to use a slightly wider range to that of an Earth-like, because we can have a hot water world, definitely. Right, and then the mass of the planet. needs to be less than. Just Google that a minute. Water world mass range. Okay, so ocean worlds generally have about 4 Earth radii. What is their mass? That's the question. Actually, I have a calculator for that, don't I? So if we stick mantle density at 1,000, so a planet with 4 times Earth's mass will give us a radius of around about 15,000 kilometers. Assuming a mantle density of 1,000 kilograms per meter cubed, which is the equivalent of water. And that is Earth radius of about 3 and a bit. I think we need a mass of 10 times Earth to really be able to make it a water world. And even that's giving us a fairly conservative planetary radius. Not quite Zelaf. So if it's over 350, and that's like well beyond the boiling point of water, I think. Hang on. What's that? So 350 Kelvin, 76 degrees C. So to be honest, we might as well make that 350. Yeah, so if it's less than 76 degrees C, then there's a chance that it's a water world. If it's within the temperature and mass range, and I suppose, to be honest, we may as well just bridge the gap equally between these two types. So 250 Kelvin, and that is minus 23 degrees C. Which is fine, because you can have water worlds with frozen crusts. Yeah, rotation speed is one of the last things we set. So again, this is the puffy, large atmosphere, dense ocean type of water world, not the Earth with no islands type of water world. They're like mini Neptunes. So on that note, we need the mass. So this is a huge number. If we run with that number for now, and then we'll see what kind of results we get with it. That might need refining, but that's basically, if it's in the right temperature range and it's less than 10 Earth masses, then we'll call it a water world. I think that's all of the planet types covered. I don't think I'm missing any. Did we remove Dwarf Planet? No, we didn't remove Dwarf Planet. Okay, so where to put that? I suppose logically kind of needs to go before Earthlights, but after lava planets. So if our mass is below our mass cutoff, which, scroll down my spreadsheet. So the mass for a dwarf planet is equal to that of the moon. That's our cutoff. Should squeeze in nicely there. So dealing with the temperature for lava planets, we are sorting out dwarf planets before moving on, and then these guys can be any size really. Okay, that works. Right, that should be all of the planet types. And it's got a whole bunch of output pins that we don't need. Okay, that should be our planet data done. So the last step in the process there is to add all this data together to actually form the description of the planet. And then, so I guess all of this can all get collapsed into a single node. Construct planet object. This is the last thing we do in the process. Why does it keep highlighting that? Yes, there is a conversion on the sensors. So, in fact, you can see it here where we add the data. Right here, you can see that it has the temperature in Kelvin, C, and Fahrenheit. That's good to hear, Triple Helix. Always happy to inspire people to create. So this is an absolute mess. What happens when you have large enumerators? You have lots and lots and lots of options to fill in. I will collapse a bunch of this to subnodes. Because actually some of this data here, you know, we're doing things like we're setting up the orbit of the planet, and that's the sort of thing we should be doing separately before we just go to the relatively simple task of just building the planet object itself. So really, the only thing we should be doing here is descriptions and stuff, not the orbital properties. Speaking of the orbital properties, something I'm going to do is, rather than creating big old descriptions like this for all of the data, I think what I'm going to do is maybe input the actual strings separately, and then construct them where they're actually needed on the sensors from here, rather than doing it like this here. So it's like a wall of text, because then on the sensors UI I can split that data up into separate boxes. Because it would be nice if we had things like the orbital characteristics displayed separately in a separate container box than like the high level descriptions. before I do that, I think we might be in a position to test this. Look how much smaller this is now. I do love condensing these things down. Yeah, the distance to the ship is something which is fairly dynamic. I think that is held on there. Okay, let's find out. Oh, yeah. So some of these things obviously had some of the old enum data, so I'll just refresh all of those. Just making sure we've got the right classes added to everything here. Should be okay. Oh, yeah, lots of broken stuff. That's an interesting point, actually. These are the arrival distances for the autopilot. We haven't hooked up the LT and Y class stars since adding those, so I think we will treat them as gas giants because they are practically that size. Same here as well. Probably also do that for water worlds, actually. Given their increased size. Right, what else is broke? That one, that one. Message right there. That one. Yeah, when I actually redo the readouts, I will try and make it a lot more kind of human readable. No, scales will be expressed in bananas. Oh, now what's wrong? Right then, let's see how absolutely trash the galaxy is. Just missed the question about the home key. Yeah, I'll fix that in a sec. Well, I'm expecting the planets to be new and more varied, but what's probably going to happen is that it's all going to be messed up, because it's always the case when you first do something. Right then, Alpha Centauri. It has planets. An star has a gas giant. One has planets. So immediately I'm seeing that there isn't much in the way of planets. Like, most of these have just got a single gas giant, and that's it. Now I'm assuming the reason for this is because the protoplanetary disk mass is too small, or planets are taking up too much mass from the mass pool. Very interesting though. What was that white class star? Let's go and see whether that's within the star or not. Why are they all down there? Yeah, and carbon planets and essentially the cores of gas giants where the atmosphere has been ripped away, they'll definitely be in the game as specialty items. So alongside the... yeah, exactly that. So alongside the usual array of planets and things, we definitely want that percentage chance for something abnormal, which is kind of where the excitement of exploration needs to come into it. It's like, is there going to be something weird here? Okay, so there's a planet in front of me. Yeah, like an alcohol nebula. I think the holo display's got moved down. Right, so what data do we have? Do we even have any data? Do we? Yeah, so there's a few data issues there. Is it scanning that or the system? So this is all good. That's just a rounding error, so that needs to have decimal places added to it. Yeah, and when I display the mass, I need to make sure that I convert that to a condensed version of it, so that it's not just a string of numbers. Else though looks alright. All the kilograms. So I think what's happening here is that planets are being given too much mass. Right. Let's see what's going on with it. So when it comes to data, yeah, so those data points are not actually they're not part of the data package. And obviously we're adding them on the description, but we're not storing them as data, so that's something I need to do. So this bit worked. So the mass it's literally just kilograms at the moment. So that's fine. Volume. It's fine. Density. Definitely reading the correct variables, so I have a suspicion we might be getting some weird decimals, but it's not rounding the number, so we should be seeing some fractional digits. Let's put them there just to be sure. That one. That's fine. That one's fine, although I think we quite need decimals on that much kilograms. You are quite right. This is the worst blueprint of all of them. And that's because of these giant enums. I don't think it's possible to like collapse the ones you don't use. Yeah. Not quite sure how you would do a select on an enum if that enum had a couple of thousand options. I don't see how that would be in any way viable. so when we're determining our planet's mass, we are timesing it by 10 to the power 24. Because this is the shortened version. And then we're deducting that from the system mass. That minus that. So unless this isn't 10 to the 24, or unless that's not 10 to the 24, let's just check the star themselves. So we're looking at a G class. So oh, yes, that's what we're... Oh, no, hang on. No, that isn't. No, that is right. So... So the mass of Sol is that. Just so happens on my handy dandy spreadsheet that I've got Sol's mass there, so that one's times 10 to the power 30. Oh, because we're using 1.989. So if I do that times 10 to the power 24, it should be the same number. Definitely the right amount of kilograms. And then the percentage of Sol, so yeah, so it's 0.9 to 1.06. Multiplied by that times to the power of that. That gives us the mass of the star, which is huge. Right, then when we calculate our system mass, we take that value I wonder if it's the random stream here, so if we take that value and times it by multiplier, that gives us that much. Then we have so we still got plenty of mass, because even if we have Jupiter so I suppose in this instance Jupiter is taking up 70% of the mass budget, which I think is actually accurate. So that divided by that, 73%. Yeah, so that is actually correct for the Solar System. Jupiter does use about 70% of the mass up. So is it the case then that we're actually on the random stream picking just really low numbers all the time and then generating gas giants, which are then just chewing up all of that mass? Or is it the case that they're getting too much mass? So, looking at my test data, I'm definitely using 10 to the power 24 for Earth. It should be 5.97. And if we look at let's get rid of some of this a minute. So for Rocky, we're going up to 11 times 10 to the 20 times 10 to the power 24. So it's in the right ballpark range. Obviously, gas giants are massive. So is that number the problem? Are we literally just chewing up the mass pool immediately? Would be. So when generating these gas giants, so if the random picked the maximum value there, that's 24 times almost the mass of the entire solar system, which is a huge amount of mass, and even half of that is still considerably more mass than is in the entire solar system. So because that's 13 Jupiter masses, which is the borderline between Jupiter and a brown dwarf. But what we don't want is for the random to be picking massive values like that all the time. Because Jupiter is only, what was it, 300 and something? Yeah, 317 would be Jupiter, and that's 24,000. So, kind of need to we need to define this as a sliding scale based on the mass of the star. Or rather, the size of the mass pool. No, mass of the star, because that's a constant value. So, if we take the mass of our star, yeah, so we've got our mass pool, which is a percentage of the star's mass, a very tiny percentage, which is based on Sol system as our kind of example. So what we need to do, we kind of need to map a range on that. What we can't have is like an M-class star with practically a brown dwarf next to it, because we can handle that scenario when we do binaries. But a really high mass protoplanetary disk, like on a B-class star, is going to have enough mass where it can swallow up brown dwarfs quite happily. Right, so let's just work out what those mass ranges are a minute. So if we have a look at an O class, so on an O class star, we're capping at 85 times the mass of Sol. So if we do that times 85, that's our absolute upper limit. Which is a huge number. Let's remove those commas if I can. Get rid of that. Not easily, though. Okay. Right, and then at the other end of the spectrum, we've got a Y-class star where 0.01 of Sol . 0.01. Right, so that's kind of the mass range of stars. So we kind of need to use that here. So that's our minimum. Not even sure a 64-bit double can have a number this big, but let's find out. Almost. Right, so then what we're doing is we're taking our minimum and maximum values and increasing them accordingly. So we want our maximum value, i.e. 13 Jupiters, to be at the absolute top range of the star mass. and then we want to bring that right down to something sensible, with a reasonably massed star. So 11.94 is 2 Earth. So we make that 10 Earth. So if we times that by 5. So that means that a Y-class star, it's not realistically going to generate massive gas giants because its mass pool is tiny. Hey Alan, welcome to the stream. Good to see you again. Sorry to hear you had a crappy day today. Right, let's see whether this works. Hopefully we should have a much wider array of planets now. It's an interesting balancing act because there's no cap on how many planets can generate on a system. So if the star system continually chooses not to use up the mass with tiny planets, you could end up with hundreds of tiny planets. And we'll know whether that's happened when I click this button, and we'll see whether or not we get an infinite loop detected. Okay, fingers crossed. Ooh. Okay, that's more like it. We're starting to see some planets. So yeah, it looks like I just need to tweak the maximum for those gas giants. It's like it's making loads of ice giants in this system. You're right. We don't know what's normal. It might be the case that the Sol system has a tiny amount of planets, relative to the rest of the galaxy. I need to fix that as well, don't I? Like, some of these systems are looking really good. So 1, 2, 3, 4, 5, 6, 7, 8, so it's equal to Sol. Yeah, so this is the kind of arrangement you want to see. You know, rocky planets, then moving on to gas giants, and then the icy bodies. So that was looking good. That's an interesting one, lots of stuff there. Let's go check that one out. It's there's a lot there. There's a planet. And there's another planet. Okay, so surely they are lava planets. I need to adjust the numbers for crust depth, because that's mental. You wouldn't have an 1800 kilometer thick crust. Other values look okay. So obviously volume and density are wrong. Oh, I think I know where the density's wrong, because it's I've split the density up now, so that's explained. Other than that, that doesn't look terrible. So, what about the gas giants? Is that not the gas giant? There we go, class 1 gas giant. All the mass. One Kelvin. That's not right. Need to fix this hollow display so we can have a good look at these planets. They're all going to be in the floor, I think. Let's fix that a minute. Why are you all the way down there? I actually need to know what the Z height is in the world distance, because is it 150? I suppose it must have been 140. Yeah, 140. I should put it back ish where it was. No, okay, not 140. What was your height? Yeah, she's called Ava. I don't seem to be taking the vertical height into account anywhere there, so what I'm going to do is just plonk it kind of back up where it was. Was that 250 before? Right. It's more like what it was. Yeah, the holo display, sometimes Unreal kind of freezes and does weird stuff. And if you have something highlighted like that, and you happen to move the mouse, then it will reset the object. In fact, it has reset it completely, because it should also have a rotation of 180. Actually see where it's moved to because the screen's in the wrong place. Yeah, so for some reason the actor reset, and that's just Unreal being Unreal. Right, before we hop back in, let me just change this again. So Earth is 5.97. So if we times that by 100, let's say, so yeah, so it means 100 Earths is our low end maximum for a gas giant on a Y class star, all the way up to huge on an O class. These are the kind of tweaks which change the whole galaxy, because like changing one value there means that the ranges of generation change for every single star. So these are the sort of things you refine and get right, and then set in stone and never touch them again. Yeah, I'm going to add like a little floating control panel for the holo display. Literally hologrammatic controls that spawn with the display. So you can do things like rotate the planet and change layer views and that sort of thing. Rotating it for things like the long range display would be really confusing, because it's oriented specifically with the ship. But where it makes sense to rotate it, yes, we definitely will. Right, that's better. That's where it should be. So Alpha Centauri is still generating a whole bunch of stuff. This is that one. Oh look, Sirius is generating a gas giant right up against the star. That Sounds like it's worth having a look at. Ooh, some weird stuff going on there. Wait, is that a gas giant on top of the star? Surely not. It is, isn't it? Wow. Out of interest, how big is that gas giant? Okay, so it's got a radius of 1.8 million kilometers. What's Jupiter's radius? Jupiter radius. Oh, nowhere near. So we're dealing with a truly enormous gas giant there, and probably far beyond what's possible. So, I think I know what that is as well. I think we're not actually setting the mass for those yet. Let's throw through it and have a look. Yeah, that's what I thought, Aaron, because as the mass increases, obviously it compresses more. So, you know, even to the point of a Y-class star, they're only just bigger than Jupiter, so a planet this large shouldn't be possible. It's about to get very bright, isn't it? Yeah, so that gas giant is actually bigger than Sirius. Right, what else do we have in this system? I think the other issue is all the planets seem to be on top of each other. Right, okay, so I think mass-wise we're probably okay, but we do need to have a look at the densities, I think, for the gas giants, and if memory serves, I don't think I've done them yet. Yeah, I haven't. So Jupiter's density is 1.33. So if we move that down a bit. I wonder what the mass fraction is on Jupiter. So core mass fraction. These things are never easy to find out. Yeah, so you get things like this. So core mass fraction. Mass fraction, okay. I think that's the mass fraction we're looking for. I'm going to have to do some digging and some gas giant data there. Yeah, I got a plugin on the last Epic Marketplace sale that there's a tool which allows you to do light probes on any surface, which is perfect because we can just probe the amount of light coming into the window and polarize the glass accordingly. Nice and simple. I need to have a spare 5 minutes to implement it. Or, as is usually the case, deconstruct the plugin into its component parts, rip it apart and rewrite it myself. I think what I will do might have to just set these values manually for a minute. Just so that they're not all zero, so that's the issue. We're using zero density values. So Jupiter's core density is around about 25,000 kilograms. The rest of it is about 1,300. It's a very low density planet. I suppose I better check Neptune separately. Neptune's slightly more dense at 1.64. Uranus is 1.27. And Saturn is 0.7. Wow, Saturn's just a big ball of fluff. Okay, well 1.3 is kind of midpoint, so we'll leave that. Right, so if you set those for the densities literally just as a temporary measure, so that they're not broken, and then on the mass fraction, we also need to calculate those. So if we set really have a crust, but the data is expecting one, so we'll give it one. So if we do, I believe, 0.25, do that as 0.74 plus the extra 1. Plug both of those into there. That's literally just a ballpark figure. That should at the very least stop gas giants being super weird. Right, so I've just realised the problem with the planets all appearing on top of each other is because these values have been reduced to the standardised units. So things like the mass is in kilograms, distances are in kilometres. So of course the game is treating kilometres as centimetres when they should be centimetres, which means I need to multiply all of the kilometre values by 1 million, I think. Kilometre to centimetre. No, 100,000. So all the distances are 100,000 units wrong. Right, so are we... Rather, where are we doing that? So, in the solar system, right, so where we spawn the objects. Actually, that's before that, isn't it? So that would be here. So that's when we're doing our orbital characteristics. So we're taking that's in kilometers, which means all of these are in kilometers. Right, so really I need to multiply that. That by 100,000. Right. Sure that is correct. Yep. Okay. Right, so hopefully that's fixed the distances and the gas giants being weird. Stephen House, yeah, definitely. Ryan, yeah, I actually went through the whole process at the very start of this stream. So if you want to rewatch the stream from the beginning, you'll see the star system formation process in detail. But in a nutshell, yes, we model every aspect of the system in a protoplanetary disk. Yep, we have salt planets, that's good. Don't have our temperature regions, so there's a kilometer to centimeter issue there. Alpha Centauri still has a bunch of planets. So Sirius was the one that was seriously a problem. So let's go and have a look at that. Okay. Oh, yeah, things seem to be where they should be. That's good. Yeah, no worries. I don't expect people to watch a almost 4-hour stream. Actually, that's a good point. It's been nearly 4 hours. Claire will be chastising me on the length of the stream again. Aha! We have a star system. So it looks like this star system's about 20 AU in size. We've got planets all the way into there. Let's just check the data on these a bit. Right, that's more like it. The radius is what it should be. It's no longer millions of kilometers. Let's just check this one. This one's a super Earth. It's pretty big. So I'm going to have to add a lot of the data points that we're generating onto here as readouts, if for no other reason than to sort of debug and troubleshoot the planet generation. Because I'm questioning if the radius is 11,000 kilometers, which is double that of Earth, then why is the gravity only 0.3 of Earth's gravity? That doesn't sound quite right. So that needs investigating. Yeah, the density must be crazy low. Well, the actual density is 0, but that's because that's using an old variable. So what I'll do is I'll add the various density layers separately, so we can see the density of the core and the mantle and the crust, and be able to just sanity check the data. It might be the case that it's not generating enough density for the mass of the planet. So obviously the mass is just a value that we're choosing randomly within a range, and then we're deriving everything from that mass. So kind of the mass is the ground truth. So things like the core density and the mantle density, and therefore the radii and volume, should be relevant and consistent to the mass of the planet. And they're not quite by the looks of things, so I think it's probably the case that it's not, like, the density value needs to be higher. The density's in layers, so it's got the core, the mantle, and the crust. For gas giants, the crust is essentially the upper cloud layer. But we'll be removing the crust for gas giants, and it will just have core and mantle. So yeah, see this one as well. This planet feels too big. I mean, we know that super Earths and mini Neptunes are the norm in terms of the exoplanet data we have. So we should expect there to be more super Earths than normal Earths and more mini Neptunes than Neptunes. That's just a given. But that doesn't look quite right. Let's go and have a look at it and see what it actually looks like. Right, hold your breath, we're flying through a star. Oh. No, we're not. I didn't press the button. Oh no, we are still flying through the star. That was the worst approach in the history of approaches. That was kind of like, it was either a loop of shame or it was a Tokyo drift of awesome. One of the two. Atmosphere is crazy thin on this world. Just check that it actually works here. Beep. Yep. Okay, well, I've got a few things, obviously, that need to be tweaked and sanity checked there. So I think I'm going to go and take a break and then get on with that. So don't expect dev build tonight. I will focus on getting one out tomorrow. Obviously, once all that's all fixed and polished and working a little bit more reliably. So yeah, I think with that I shall bring the stream to a close because it's been 4 hours and I fancy a shower, so I think I shall go and do that. Thanks Fitzbrain. Yeah, so I'll go and do a bit of research, do a bit of tweaking. I'll get those data points onto the sensors so that we can sanity check things properly. And then we'll take it from there. So yeah, catch you on Wednesday stream, 8 PM, usual time, and hopefully I'll have a dev build out tomorrow. Thanks again everyone, bye for now.